So let's talk about transient luminous events and the relation to these horizontally extensive flashes. Earlier I talked about how cloud flashes can lead to gigantic jets and blue jets, blue starters, and that's just in a matter of extension of the leader network that extends outside of the thunderstorm and propagates up into the rarefied air, becoming a streamer. In the case of a gigantic jet, that's a negative streamer from a negative leader. And in the case of a blue jet, it's a positive leader that transitions to a positive streamer. Now we're going to look at sprites and the mechanism behind their formation and in relation to horizontally extensive flashes. And the primary driver for sprites is a positive CG flash in which there's a positive CG return stroke, extensive negative leader development in the positive charge region that follows that return stroke, or as a result of that return stroke, creating a very intense electric field change. And that electric field change then results in the development of bidirectional streamer activity in the upper atmosphere. The ionosphere is positively charged, and so when you introduce a large negative charge or electric field change in which negative charge is increased in the lower atmosphere, you increase that electric field and to the point where we see breakdown in the upper atmosphere. And again, sprites are not connected to the storm in any way. Here's an example of a sprite by Hank Shima. You can see that you have both upward propagating or branching streamers as well as downward propagating. And in this case then, since the ionosphere is positive, these would be negative streamers going up and positive streamers going down in response to that electric field change. You can see this in high-speed imagery. You're going to see the triggering flash brightness near the horizon and then response as the streamers form. And you can see you get multi-direction development of these streamer heads in response to the electric field change. On one occasion when I was out filming, I got the chance to film both sprites and aurora during this particular storm in western South Dakota. And it was quite an event to behold, but I was treated to a lot of color that night. And what was interesting is this is the first time I was also able to capture what are known as ghosts. And these were first identified by Hank Shima and Paul Smith, and they were able to identify that these are true phenomena that we're seeing in relation to sprites, emission in the very narrow green spectrum, and they came up with the name of ghosts. And so the term ghost the abbreviation GHOST stands for green emissions of excited oxygen from sprite tops. And so a good acronym, and they are kind of ghostly when you see them because they tend to linger a little bit longer than the sprite and have that eerie green emission. Here's an example video from the same storm and those ghosts that were produced that night. There were a handful of ghosts that occurred. See how it kind of lingers behind. And recent studies have looked at that green emission and also attribute it to metals in the upper atmosphere, nickel and other metallic gases that are actually creating the emission and causing that to linger beyond the duration of the actual sprite itself. There's an example of a dancing sprite. And here's kind of an image stack from a number of sprites that occurred over a time span of this event. So you can see it was quite prolific in producing sprites that evening. So again, if we consider horizontally extensive flashes, these are the flashes that not only can initiate upward leaders from tall objects, but they can also initiate sprites. And again, it could be the same mechanism, the positive CG return stroke, that is the driver behind the initiation of the sprite. So in this case, we look at an example where you have an IC flash that decays, positive leader develops, causes a positive CG return stroke, and it's this return stroke that, in fact, initiates the sprite. Again, sprites are very short duration, a matter of milliseconds, whereas the upward leader and the lightning flash itself is much longer than that. Well, we've talked about a number of TLEs already, including the gigantic jet, blue starter, sprites, and ghosts. But there are a few others to talk about. Associated with some sprites is a kind of diffuse area near the top of the sprite called a halo. And there's also a thing called an ELV, which I need to read it's an acronym, but I need to read it because I just, for the life of me, can't memorize it, which is the emission of light and very low frequency perturbations due to electromagnetic pulse sources. So what that means is that this is not due to an electric field change. It is due to electromagnetic pulse that comes from a very intense flash from below. And these are kind of circular. They're very large in diameter, and they spread out as a donut from a central source over the point at which the electromagnetic pulse occurred from the lightning flash. And they're very fleeting and very faint. Now, lastly, I want to talk about secondary jets. And these are events that occur in the lower portion of the upper atmosphere, more near the cloud, thunderstorm cloud itself. And these can involve things that look similar to sprites and behave like sprites, and they also can have like an upward component similar to a gigantic jet. Now, these have been observed in studies since around the mid-2000, 2005, 2008 time frame, when they were classified. Essentially, what the proposal that was made in the literature was that when you have an intense sprite, you essentially are moving charge. You have an upward movement of electrons towards the positively charged ionosphere. You have a downward movement of positive charge due to that upward movement of electrons. And so you've essentially lowered some positive charge as a result of this sprite and kind of created a new layer where you have a positive charge region and this negative charge that was established due to the CG flash that occurred and triggered the original sprite. And due to this reduced distance and introduction of this positive charge layer lower in the atmosphere, it may cause a reinitiation of a sprite-like event in the lower portion. And so you get this redevelopment in the lower altitudes in between these two charge regions due to the intensity of the positive CG flash, or continued development of the negative leader, or subsequent the positive CG return stroke that is that again causes that electric field change to once again drive another event, but it's lower due to the previous influence of the sprite that preceded it. And in the case where we see upward propagating jets in association with that, that could be in itself a continuation of the negative leader activity that's going on inside the cloud, and some portion of that negative leader then does extend out of the cloud and become a streamer and move upward just like a regular a gigantic jet, but in a smaller scale and in response to secondary activity and a previous electric field change and charge rearrangement due to that first sprite. So these are kind of the family of TLEs. I'm not an expert in this field of study. This is outside my area of expertise, but this is what is generally understood to be true and looked at by the scientists and reported in the literature. So now that we better understand transient luminous events, in this next section we're going to take a look at thunder and how it develops in relation to leader and return stroke development. And then we'll look at damage caused by lightning.